right? We did even print it on textile, cotton textile, and we coated with some layers, and it was washable. So we were able to wash this textile for 50 times in the normal laundry wash, and it survived it. The battery was still cycling. This is some of the performance of the battery, and you can see basically the initial capacity was around 1200 or above 1200 milliamp hour per gram, and it survived for a couple of more than 100 cycles, and it's also survived more than 100 cycles of bending and twisting. Simply because the way this material grows is it bends itself very well to the fibers of the textile. Well, lots of you are chemists, so most of this cotton textile have OH group and some functional groups on the surface, and it really linked well or reacted chemically and formed some covalent bond with the tin oxides that we forming basically one single compound between the textile and the active material, which make it highly performing, and the adhesion between them is quite high, which basically allow the stability electrochemically and chemically as well. That's some of the examples we do work on. However, as much as it is good and promote clean energy, promote also clean energy not only in the term of storage for grid applications, but obviously for transport applications and for electronics. Well, simply without lithium-ion battery, we cannot live. We will basically back at least 100 years backward in technology. And obviously this guy, still alive, still writing papers surprisingly after 102 years now. He's 102 this August. So, but you can see actually from here, even people knows how important it is. It took around 40 years for him to get a Nobel Prize, which is quite a lot, I would say, for an invention like that. But regardless, we cannot continue using lithium for so many reasons. Not only because of the technology of the battery itself, but mainly for political and economical reasons. We run out of lithium around the world, and the fact that the commercial batteries we do have is mainly using NMC, nickel, cobalt, manganese, and most of these elements are produced in very particular countries in Central Africa that make mining of them pretty much subjected to political situation, which is usually not very decent in Central Africa anyway, and because these countries as well cannot really or do not really have port on the sea, so they must have a good relationship with their neighbor countries. Very challenging. Anyway, in terms of the supply chain, this is unreliable. In terms of nickel and cobalt, and most of the European countries who used to produce nickel and cobalt and also manganese has phased out this kind of mining because of environmental reasons. Anyway, so John Goodenough himself, when he invented the battery, did not invent the lithium-ion battery first. He invented sodium-ion battery, actually. So he himself suggested, go back to sodium, guys. If you have problem with lithium, well, sodium is everywhere in every ocean and every sea, so we will never have any problem with sodium. But the problem with sodium, it has lots of technical problems again, that we cannot really carefully use it in the term of either sodium metal or sodium ion version. Sodium air, probably one of the solutions to do that. But again, for health and safety reasons, most of the companies, particularly electronic companies, will never think of even using sodium batteries, ions, or metal in their handheld devices. Maybe in large scale grid applications, it's useful. Same as for sodium sulfur, which is the main battery for energy storage in grids anyway. But for handheld devices, no way. And also, there are very good, or let us say, trend between scientists right now to try to use cheaper metals and more available metals such as nickel and zinc in particular. I am very advocate of zinc batteries and aluminum batteries as well as a rechargeable batteries. Obviously, the energy density and the power density may not be as good as in lithium, but it's everywhere. We don't have any problem with the supply, and it doesn't have any safety problem. Really, even better safety-wise than lithium, I would say. All right. most of them, unfortunately, struggling technical problems related to, as you know, most of these ions are way bigger or larger than the lithium, twice or even more than that, makes it basically so difficult to find an electrode material that can survive the volume change between a charge and discharge. And also, because of the potential or the electrochemical windows, most of these electrodes actually lead to the decomposition of the electrolyte itself, no matter what kind of electrolytes we used. So we're still far away from using them commercially, but we are in that way. Depends on basically what kind of applications again. This is some of our research, basically, because I am now more focused on designing more universal electrode, an electrode or active material that can be used in more than one system. And Yulk shell structures are usually my favorite. Yulk shell structure is like an egg, basically. The shell of it is made of hard carbon, very porous as well. And then we have a little bit of active material in the core of the structure. So there is around 70% vacuum inside the structure itself, beside a very conductive shell on the surface made of carbon, which simply means I can accommodate the volumetric exchange during the charge and discharge. So we designed a couple of these structures with different material for both anode and cathode. The same principle really applied for them. So it's easier than what you think, really. So what we produce is a spherical structure of oxides, usually, and then we leach the oxides by sulfuric acid or hydrochloric acid or anything, coated by carbon, usually polymeric carbon, and then carbonize it under nitrogen or argon to form the hard shell that we want, and then selenide it or convert the oxides, if we want, to any other structure, such as, in this particular case, the dichalcogenides, or some carbides or some nitrides or phosphides, different structures really, and different type of compounds that we did really try. Probably over 30 compounds we tried in our lab in Yulk shell structures. But again, when we tested this material in lithium, we really achieved over 50 cycles with Coulombic efficiency over 89, and also that's with selenides. In sodium is still performing very well, reaching a record really for that. And also potassium in particular, which is the biggest ion of all this alkaline metal, could reach to over 200 and 100 cycles, depends on the current rate. We did more open structure when we anchor nano dots or quantum dots of the selenides and dichalcogenides and sulfides, here in particular on graphene nanostructure. Again, the performance is even better, and we could cycle it for over 500 cycles in sodium batteries, and also some very good achievement with potassium batteries. I forgot how many cycles we did it with potassium, this one, but I believe also over 200 or 300 batteries. This is one of our work for sodium sulfur, and we do work a lot on sodium sulfur, particularly regarding to molten salt batteries, because that's where we come from. And this is a design basically where we loaded the sulfur into a porous sponge-like structure made of graphene, or made of graphitic material from polymer sponge, normal polymer sponge. We did it even with kitchen sponge, like the normal kitchen sponge. We polymerize it, we did graphitize it and fill it with sulfur, and it's always depend on how we load the sulfur into the carbon. So you can see the bottom one, the blue one, is actually the one loaded by just elemental sulfur directly impregnated into the sponge. And you can see it's actually the lowest of the performance, simply because it deposits on the surface only of the porous structure. But when we basically try to load this elemental sulfur from solutions, it basically go deep inside the porous and nanoporous basically of the sponge, and giving obviously higher performance as well. Despite of this success of and lots of research as well in liquid state, not liquid state, but liquid electrolyte. There are lots of problems still available with liquid electrolyte. And particularly now, when we switch it from just using the batteries in handheld devices or even in grid applications, now batteries are going to be the main, and lithium batteries are going to be the main driver for the electric cars and electric vehicles in general. And there is a trend to basically convert everything into electrics. UK, for example, has a government plan to phase out all the fossil fuels cars by 2030. Not quite sure that will happen. But in all cases, electric cars are everywhere now, and sooner or later, it will phase out the fossil fuels car. E-scooters, for example, endless bikes, electric bikes everywhere. It's hard even to find the normal pedal bikes now without this hybrid system of batteries. And those guys are really struggling because the traditional battery has not been designed for this kind of mechanical shock and mechanical vibration and mechanical load that a car could have. So any car that would have any accident will really release huge amount of electrolytes that make of organic solvent very damaging. And it's very difficult to remove from the road because, for example, if any fossil fuel car has an accident, you would probably have some leak of the fuel, but this one will evaporate quite quickly and will be limited to some very tiny little area around the car. This one, the organic solvent in batteries, if the car had any accident, could be there on the asphalt for at least a couple of days. And it's very flammable. The flashing point of it is very high, make it literally a bump in the road. And if you have a couple of them, then certainly you have huge problems. Considering also most of these cars are really heavy and using energy because of its electronics, it produces huge amount of heat inside the battery itself, which simply make the battery as well by itself a source of danger or risk. The size of the Tesla battery is almost that size, almost 1/4 of the size of the car. Going to improve in the future, obviously, because they want to store more energy and run the car for even longer. But you can imagine. And the driver is actually sitting next to this bump, as I call it myself. So there is, I think, or a way, or people trying to switch from using organic electrolytes to solid-state electrolytes. Obviously, this is not a new research. Solid-state electrolytes was as old as lithium-ion battery itself, and lots of ceramic material has been developed for as a lithium conductors. And also many of these solid electrolytes are coming from either the fuel cell research or also from the reverse osmosis for water desalination as a sodium ion conductors as well. So it's a mature industry, but when we adopt it in lithium solid-state battery, we have so many technical problems, including, for example, the kinetics of, or the sluggish movement of the ions, and also the problems at the interface between the electrode and the electrolyte. There is also polymer electrolytes, which is usually used some sort of conductive polymers, ionic conductive polymers. And this one again had the same problems of at the interface between the electrode and the electrolyte, and also the transport of the ion inside the electrolyte itself. To overcome that, people thought of different methods, obviously, improve the conductivity, reduce the resistivity, improve the impedance of the polymer, make the polymer itself from a couple of segments that allow the polymer to move faster. But another thing we did try is to basically add already or mix both ceramic batteries or ceramic conductors with the polymer instead, or within the polymers, including our work of basically using randomly oriented clay or silicate mineral that basically work as a conductor for the silicon and the ions as well. But this one we struggled with a little bit because the randomly oriented crystals would basically leading to some sort of nitrate formation and non-homogeneous distribution of the charge on the surface. We modified it a little bit by vertically aligned layered clay, which significantly improved the battery performance and reduced the resistivity of the material. You can see that, and also improved the lithium transport number from 0.2 to 0.8. So 4 times better transport of lithium at the same time. Add to that, obviously, because it's clay, it's improved the mechanical properties of the battery and the stability of it. You can see from the last performance one, the cell was polymer electrolyte without our vertically aligned MMT, survived for only 200 cycles, while when we add this vertically aligned clay, it moved to almost over 500 cycles. This is also one of our work when we used the polymer electrolyte, but this time we played together with modifying the electrolyte, with modifying the cathode itself. We add BVF to the cathode, which basically attracted an ion to come to the cathode. Very strange for anyone who knows electrochemistry anyway. But by doing that, we basically, what we can say, introduced the concept of dual ions to the battery. So basically, instead of transferring and storing the energy by lithium only, we use an ion as well to store the energy in the same time, which basically doubled the capacity of the battery and improved a little bit of the conductivity, reaching, as you can see, to around 400 or 4,000 cycles, which is quite a record for polymer batteries. Still struggle because this concept, as good as it looks like, it actually promoted the dissolution of the cathode, which simply means we have kind of gradual decay of the battery performance anyway. But we're still working in that. Hopefully we'll improve it in the future. This is another battery very similar to the lithium air battery, but instead of using air or oxygen, we're using CO2. So basically, the whole idea, as you can see from this cartoon there, is during the discharge, lithium ions will go to the cathode, which is made of catalyst, right? And that's basically where we work. We designed this catalyst, and when you have molecular CO2, it basically, by this catalyst, to convert into carbonate, react with the lithium ion to form lithium carbonate, which during the charging go into the anode made of either lithium metal or lithium compounds to basically decompose again to lithium and CO2. So it basically use the CO2 as the fuel for the battery itself. We did lots of work, including using electrolyte made of molten salt, because that's simply improved the capacity of the battery and also removed lots of kinetic problems on the cathode. Because the problem with the cathode, with the catalyst, you form lots of carbonate on it, and this carbonate block the battery after a while. So to avoid that, molten salt simply dissolve this carbonate straight away. This carbonate layer or oxide layer, they dissolve it, the molten salt dissolve it straight away into the battery, improving the capacity of the battery. We found actually this method could be used to produce very good, nice graphene and carbon nano material when we use some particular catalyst, such as nickel in this particular case. These are some of our publications in the area. There is no conclusion with batteries, by the way. We will always continue to do batteries. I do not see that we will use any other energy storage for the next 20 or 30 years. But I believe myself, and I was advising the British government about the trends for batteries in the future, that more likely the research will focus on developing universal material or designs for the electrodes that can be used in more than one system, simply because we will be forced sooner or later to switch from lithium to beyond lithium. And beyond the lithium, I would think myself the new future or the new designs will be mainly magnesium and zinc, more than any other things, for different reasons, including obviously the price, but also the simplicity of manufacturing them. And obviously zinc and also magnesium are very well matured industry anyway around the world. Yolk shell structure will be obviously at the core of this development, because it's one of the few designs or one of the few structures that will allow to accommodate this large change in the volumes in the electrode. Solid state battery, whether or not we like it, despite all the technical problems that does have, will soon become predominant, particularly for electric vehicles. And metal battery is soon to be replaced lithium-ion batteries. I would predict between 10 to 15 years, we will never use lithium-ion battery again. That's my prediction at least, but I can see that happening already around the world, thanks to my group and Bournemouth and Cambridge as well. And thank you for you guys. And this is hopefully an ever-expanding list of collaborators around the world. So possibly some people will join this list very soon from here. All right. And thanks to my sponsors, particularly Discolin Industries and SureScreen and Talga, because Talga is now using our patented graphene, silicon graphene, to commercialize one of the biggest or one of the first European electrodes manufacturing in Sweden. Plant 1 is using our technology to recycle plastics and use it also as a battery electrodes. All right, and thank you so much. Yes, this is actually our foam, which we used for sodium sulfur. So it's made of graphene, and as you can see, it's very light. So the entire block, one by one, is around 0.6 milligram of the material. That's why they call it aerogel, really. So you can see it stand nicely on the petals of flowers without damaging it. So I made it, of course, in a love heart, simply because it matches my name, but also just simply, to show basically we can form it in any different shape that we would like. So it's for fun, nothing really serious, but it's the same exact structure we used for sodium sulfur battery. Thank you so much, and I'm welcome any questions. Thank you.
Excuse me.
Thank you very much for this interesting and important introduction. So please, resume the information from yesterday.
Yes.
I would like to ask you a question. You already mentioned that you are suggesting different kind of batteries. Our government last year signed a contract with U.S. Millennium Challenge Corporation, a $234 million battery storage project for 200 megawatts of battery storage. So based on your expertise, what do you think would be the best way to go for listing batteries? Although they are speaking about lithium-ion batteries, according to our Minister of Economy, they left an open place for discussion about looking next 2 or 3 years what will the trend goes. So just asking you, what do you think? What would be the best solution? First question.
Yes.
And another question is, in thinking of environmental protection terms, what do you think will happen in the next 10, 15 years with those batteries? Thank you.
Oh, well, can I start with the second one? Can I start with the second one? One problem we all struggling with, and there is a huge trend of research about, including battery 2030 in Europe, is basically how to recycle lithium-ion batteries. Because we will will not end up, we already have plenty of exhausted battery that we don't know what to do with it. Recycling lithium-ion battery is not like recycling lead batteries, where basically you dealing with simple battery. Basically, considering the components here are very heterogeneous. You have metals made of the collectors, organic solvent, lots of salts of different compounds, lots of byproduct you generate during the life of the battery, and the electrodes itself. And by the end of the day, you're talking about oxides. So you don't want to spend so much money recycling them to end up by a ceramic material that freshly, very cheap. Anyway, but now I think there will be some sort of regulation that will force that the governments, every government will force the users of the battery to recycle them safely. Right? There is a research, obviously, how to recycle that, including our research as well. I have a couple of work, basically simply because molten salt allow us to heal the electrode as it is. So instead of killing the battery and trying to scrap it and try to separate the anode from the cathode, from the electrolyte, from the collectors, we use the electrode as it is and heal it. So this is a research going on, but we still work on that. In terms of the American research, the simple way is basically the best way to use this money is to manufacture the batteries here. And I was discussing with Professor Fattah yesterday that it's probably one of the best countries in the world to produce this kind of electrodes. Simply, you have the mines, you are very central next to the market, you have very good trained people to do that. So plenty of, and it does not cost much. So this 200 million could be way enough to produce the entire battery system inside the country. It doesn't really need a huge land, for example, to produce. And the regulations around recycling and the environmental protection of it is very easy to control. So that's the best way, in my opinion, to manufacturing the batteries locally here. And use it probably for building a gigafactory, 1 or 2 gigafactories inside the countries. That's in terms of the lithium batteries. Countries around you are producing around 22 gigafactory in Europe now, and also producing the electrodes is now happening in Slovakia and Slovenia, and Croatia as well is producing anodes. So assembling the battery here or producing the electrodes here is the easiest way to see it. And as I told you, it's basically, it could compete even with China. Because in China, the prices of the battery are obviously very cheap, considering the label there is quite cheap as well. So I think here they have a potential to produce that almost with comparable price to the Chinese batteries. That's in terms of that. The future, and considering also Kosovo has very rich resource of zinc, I think this should be one of the priority of the country, really. So instead of selling zinc as an ore or maximum as a metal, you can easily sell it as an end user battery of zinc storage, particularly for grid applications. I'm not going to basically lie to you that we have now current technology that we can use zinc in handheld devices like this. That will take 10 years. But producing zinc for larger scale grid applications is very possible. And probably that's something the government here should think of. But that's again, depends on what contract exactly they have with the Americans. Right? You're welcome. Yeah. Any other questions? Okay, thank you so much, and welcome.
Lexoj shkurt një biografi të tij. Është anëtar korrespondent i Akademisë Shkencave të Maqedonisë, profesor I rregullt në Institutin e Kimisë, Fakultetin e Shkencave Natyrore dhe Matematikës në Universitetin Kirill I Metodi në Shkup dhe në Departamentin e Kimisë Inorganike dhe Analitike në Universitetin e Lodzit në Poloni. Ka doktoruar në Universitetin e Zagrebit në lëmin e elektrokimisë, studimet pas doktorate si laureat I fondacionit prestigjioz Alexander von Humboldt, I ka kryer në grupin e Fritz Scholz, një shkencëtar me renome botërore në elektrokimi në Universitetin e Greifswaldit në Gjermani. Profesor Mirçeski ka publikuar 130 artikuj shkencor në lëmet ndryshme të elektrokimisë, si dhe 3 libra. Na kemi nderin sot që kemi këtu, dhe ai do të paraqitet me temën, do thënë Profesor Valentin Mirçeski from Academy of Science and Art of North Macedonia, electrocatalysis, and novel electroanalytical techniques. Nathan, please, Professor, you have to speak.
Okay, thank you very much, dear President, for the announcement. Thank you very much for the invitation, dear Professor Fettah, my dear friend. It's my great pleasure for being here, really, to be invited for the first time in the Academy. But of course, I was coming frequently, and I'm really always happy when I came in Pristina, because I feel that I come to friends, which is really very important for me. Let me now give you a presentation a little bit from a different perspective. Speaking a little bit generally about electrochemistry and so on. So I would say that if we would like to define electrochemistry in a single sentence, that would be that electrochemistry is science for electron transfer across interfaces. So that is the essential phenomena that we see in electrochemistry. And usually I would like to stress that generally that the electrochemical science has three important features. It is experimentally simple, really amazingly experimentally simple. But of course, it is profound in the intensity of the electric field, which is established at the interface between the electrode and usually electrolyte solution in which the electrode is immersed. In that microscopic dimension space, the strength of the electric field is really amazing, causing such a amazing phenomena of electron transfer across the interface. And I also would like always to stress that electrochemistry has inside a sort of beauty. You know, when we see, for instance, the typical outcome of one very common electrochemical experiment, this cyclic voltammogram, we see such a symmetry, such a cyclic behavior, such a smoothness of the data. So I say inherently, really, electrochemistry brings a beauty into the science and generally into the research and life. And you know, it is not so surprising that Pablo Picasso was inspired by electrochemistry. In last century, during 60s, you know, which is not very, very frequent case, Pablo Picasso dedicated a painting, and that was dedicated to the current stage of electrochemistry, especially of the electroanalysis, polarography, to the shape of the curves, to the arrangement of the experiment, and so on. And because I like also a little bit philosophy of the sciences, here I have looked what really other clever people have said about electrochemistry. For instance, this great astronomer, he says, you know, in each law of nature, a sort of beauty is engraved inside that law. And our strive to understand the nature, to understand the essence, how universe actually works, in which we are part of it, that tendency is also driven by some aesthetic aspects, because beside all that logic, all that reasoning, the beauty is also inside the laws that govern this universe. So electrochemistry, generally, when we speak about electrochemistry, it can be divided in two big parts. I say in two big kingdoms, you know. For instance, one is the kingdom in which energy is produced and in which the energy is stored. That is, of course, the kingdom of the battery, which are in the focus of the discussion today. But of course, there is another kingdom in which I personally belong. That is the kingdom of electroanalysis, we say. Electrochemistry and electrochemical techniques can provide really a powerful tool for analysis. chemical analysis. And that analysis can go even to the degree of a single cell, to the vicinity of the single living cell, moreover, even inside the single cell. So electrochemistry generally is really a versatile, amazing interdisciplinary science between chemistry, physics, of course, rested on the mathematics and so on. Regardless what we are going to study in electrochemistry, whether batteries or electroanalysis, the essential phenomena are practically identical. These are called electrode reactions. And the basic research actually in electrochemistry is focused somehow to understand the mechanism, the main driving forces, how this, I would repeat again, amazing phenomenon of electron transfer jumping from one to another phase is taking place. So I will now look to these electrode processes from the aspect of, let us say, more electroanalysis, from that perspective. But the principle, how we are going to think about them, are of course applicable to the battery systems as well. For instance, first, I will look even in my personal data of experimental research that I have done. For instance, to find the solid particles as electroactive materials. Usually electrochemistry, we say it is a solution chemistry. Frequently, the electroactive material somehow is inside the solution. But of course, with the battery system, the solid materials are electroactive itself. Therefore, understanding solids as electroactive particles is also important. How to study solid particles, for instance, minerals. That can be experimentally done in an easy way if we have a special, let us say, soft electrode. Soft graphite electrodes can be produced rather easily, paraffin-impregnated graphite electrodes with a soft surface in which we can mechanically attach immobilized microscopic or even macroscopic particles, for instance, of minerals, real crystal structures, minerals. These are minerals from Macedonia. And then upon externally applied electric field at the interface, at the electrode in which the solid particles is already immobilized, electrochemical transformation of minerals can take place. And with nicely selected sensitive electroanalytical techniques, we can even produce specific outcomes, we say, specific current voltage curves, usually called voltammograms in electrochemistry, which can be by morphology, by the intensity, by the position specific, and we can use them even for qualitative distinguishing of type of minerals, or let us say we use electrochemical techniques like spectroscopy techniques for qualitative analysis. In another branch of electrochemical science, not only solid crystals but alloys could be used as electroactive materials, or they can be used as a substrate for very sophisticated electroanalysis. For instance, bismuth film electrodes, in which the bismuth is electrochemically produced and deposited at the electrode surface, which then is used as a substrate for further deposition of traces of metals, zinc, cadmium, lead, and so on. The research will reveal whether we deposit one metal to another metal or we create alloys at the electrode surface, but nevertheless, after formation of this composite, we can use that material for anodic dissolution, we say, of these metals, which is very, very sensitive approach for metal detection and for metal analysis. In another branch of research, it is not necessary to use metals as electroactive materials. We can use metal, for instance, nanoparticles already electrochemically deposited at the electrode surface as catalyst. For instance, electrochemistry of copper is well known, of course. Electrolysis of copper, production, or raffination of copper, that is well known. The copper industry is based on that processes. But of course, copper is excellent, also catalyst. Here we have tried to use the copper, electrochemically deposited copper, to create sensitive sensors for detection of hydrogen peroxide. Even the idea was to detect hydrogen peroxide in the gas phase, to have such a sensitivity. And we deposit copper at the surface of carbon electrodes, and that process of copper, electrochemical copper reduction, is sensitive to the hydrogen peroxide. But moreover, as soon as we create copper film or copper nanoparticles at the electrode surface, then the copper nanoparticles are becoming really new electrodes and very sensitive, and some new mechanism which is not completely clear for us, some radical mechanism extremely sensitive for hydrogen peroxide, direct reduction at the copper nanoparticles is taking place, which is another way of using, let us say, electrochemically deposited metals as a substrate for rather specific electroanalysis. Of course, not necessarily metals are electrocatalysts. Like these ceramics, perovskites, which are not by themselves electrochemically active, they are electrochemical catalysts. Because experimentally we see that. We do not understand really the mechanism, how they conduct electrocatalysis. But the experiment clearly shows, for instance, with this material, yttrium cobaltate here, with the perovskite structure, again, this perovskite is immobilized as microcrystals at the electrode surface, and we see electrochemistry which is sensitive to chloride ions, only to chloride ions. What's going on? We can oxidize chloride ions at a lower potential, and then we have something to reduce, some sort of electrochemically created electrosorption mechanism, electrochemically created sort of chemisorption or physisorption of chlorides, or sort of chemical bond with the perovskite enables later to reduce that bond and to receive electrochemical response. In cooperation with the group from Niš for several years, I do cooperate also in this, let us say, classical subject, electrocatalysis with noble metal nanoparticles, for instance, palladium, but now not directly palladium at the electrode, but palladium on a graphene or different carbon microstructures and so on. And this is very interesting material for electrocatalysis. Of course, then depending on the structure of that electrocatalysis, depending on the how big are palladium nanoparticles, then electrocatalysis to the very basic processes like oxygen reduction, hydrogen peroxide reduction, and also hydroxide oxidation, which is important for the fuel cell. And that mechanistic analysis has been also done, which is, of course, then later for the energy producing system important generally. Metal nanoparticles are particularly interesting when they are synthesized in somehow unusual conditions, which is for the batteries also important. We had the idea to synthesize electrochemically metal nanoparticles, for instance, gold, but only at the interface between two immiscible liquids, like nitrobenzene and water. And due to spontaneous redox reaction going on just at that interface, we are able to synthesize gold nanoparticles. And then, because these gold nanoparticles now, we can orient them cleverly using hydrophobic and hydrophilic tiles, they can be oriented. And having in mind that here there is a electric, also force, electric field, which can be externally controlled, then they are becoming really a powerful electrocatalyst with respect to the really very fast electron transfer processes. Sometimes this modification could be even more sophisticated. Like this Janus particle, according to the Greek mythology, got Janus with the two faces, and this is Janus particles, again gold at the liquid-liquid interface, but we have initiated hexacyanoferrate, Prussian blue actually, electrodeposition only from the side of the water. From the side of the organic phase, we have again tile, and we have some composite, very interesting material, just as a proof of concept that we can create at the liquid-liquid interface some interesting particles. I don't claim that now they should be very useful, but as an experimental approach, that was very interesting. And electrocatalysis, I will just mention this in bioelectrochemical research, to which I'm really proud. We have recently published that after many years research actually. Direct electroanalysis in the blood serum, human blood serum, without any modification of the electrode surface, without any chemical modification of the serum, without just the blood serum in the buffer and electrode. We tested several electrodes, you see, and this is the classical example of electrocatalysis. We take basal plain pyrolytic graphite electrode, no response. Paraffin impregnated graphite electrode, no response. Glassy carbon electrode, something very weak, not distinguishable. Platinum electrode, almost nothing. If we simply take H-plane pyrolytic graphite electrode, even commercially available H-plane monocrystal oriented of graphite, pyrolytic graphite, then we see such a beautiful and strong response. Of course, in combination with nice electrochemical technique. And after several years of research, we were able to assign this voltammetric, three main voltammetric processes to uric acid, to bilirubin, and to albumin here. And so this picture so clearly demonstrates what means electrocatalysis, how the rate of electrode reactions so strongly, profoundly depends on the type of the electrode material, which is a general quest even in the batteries, of course, and in the fuel cells. So now I will distance myself a little bit from the experiments, and I will impose to myself one general question, whether it is important in electrochemical analysis, which of course is important generally for electrochemistry, whether it is important how the experiment is performed. In electrochemistry, we know we change the potential with time. The most simple way of changing potential, of course, that is the most important, linearly. We go in another direction, and that is called cyclic voltammetry, of course. But if we look in a microscopic structure of the phenomena, for any application, external application of the potential at the electrode surface, not only electron transfer takes place, which is desirable phenomena, in batteries, in electroanalysis. That is our desirable phenomena. But any externally applied potential at the electrode surface, of course, causes tremendous variation of the full environment close to the electrode surface. And then the supporting electrolyte, of course, responds accordingly, and a sort of current is flowing in the system just because of formation of, we say, electric double layer, and that current is called charging current. Our idea is to measure Faraday current, real electron transfer, but always both currents flows. But of course, it is known since long that with certain time, at the constant potential, the charging current will significantly decrease. We are going to lose the Faraday current also with time, but not so severely as the charging current. So that is why it is always good to relax a little bit, in the life and in the electrochemical experiment as well. Not changing the potential just continuously, permanently, but let us do it in a stepwise manner. We apply potential and we wait a little bit. And at the end of this step, then we measure the current when the response due to capacitive current as a priori non-avoidable phenomena will decrease. Sometimes that experiment could be done even with pulses, which can go up and down like in cyclic voltammetry. I drive the reaction in oxidation, but also in the reduction direction. And then I can come to very sophisticated, powerful technique. Pulses, but I measure the current at the end. I see oxidation, I see reduction, and the current is relatively and sometimes very clean out of the charging current, only Faradic component. So that is called square wave voltammetry, very powerful tool for studying electrode processes generally. And then I can do something which is not possible with other techniques. For instance, in electrochemistry, electrochemist knows that if they like to measure the rate of the reaction, which is critically important, critically important for batteries, then we must study the system by scan rate analysis, because scan rate analysis means simply I change the time of the electrochemical experiment. I must change the time if I like to measure the kinetics, like in chemistry generally. Here, that is possible at the constant scan rate, simply using the ability, the intensity of these pulses. And that was somehow very, very, very strange claim from us in a publication together with my colleague Kirill Lysichkov, in which we claim that we measure the electrode kinetics at a constant scan rate. And that was really a nice contribution. Sometimes when I have really clean response, clean peak, reflecting only the electron transfer. And if I go really into very low concentrations, when the signal is sometimes even not measurable, then I have right, with such a good technique, having information mainly due to real electron transfer, I can process the data, I have right to do that. For instance, simple, very primitive integration process, I can transform this peak into sigmoid curve. But this sigmoid curve, the intensity of this sigmoid curve is actually almost 2 orders of magnitude higher than the intensity of this peak here, which of course has meaning with respect to the analysis, detection of low concentrations, and so on. I was in the last several years also interested, I was somehow there or arrogant enough to say that I will suggest new techniques even. I will modify some of these state-of-the-art electroanalytical techniques like square wave voltammetry. And I have proposed several ideas, because I work a little bit more, I'm more in that system, in the theory, in the experiments, and so on. There are several ideas. I will come back here. I can suggest multi-sampling current protocol in the course of single potential pulse. I can think about simplification, or I can think about suggesting really new voltammetric techniques. We shall see how useful they would be. Here is the idea of double sampling in square wave voltammetry. Instead of sampling the time at the end of the pulse, now we have really good electronic instruments. They are really fast, and we can sample even twice, again at the end of the pulse. I can make a difference, and then I transform this already good voltammogram into so-called new double-sampled square wave voltammogram. The shape of the voltammogram, the forward, backward current, oxidation, reduction, already is better than in the original voltammogram, hoping that it will provide new insight into the mechanism of the system. Of course, I can extend that idea even to multi-sampling current protocol. My idea was to suggest the following. I do single experiment, but I have many voltammograms from the single experiment. How I'm going to do that? In square wave voltammetry, with the same good instrument, if I sample the current several times, at several points, let us say in the last half of the potential pulse, then out of the single measurement, I have several voltammograms. I analyze them and I see that they are sensitive to the electrode kinetics. So now, single measurement electrode kinetics information from a single measurement. And I'm happy, of course, to see that other people recently accepted this idea and published something with this original idea, which was really nice to be seen. Simplification. Although I'm advocating, that this technique, yes, in 5 minutes I finished, exactly in 30 minutes. Although I'm advocating, that square wave is excellent and so on, but people say this is very complicated, You understand, but for us it's not easy. So I suggest some sort of simplification. I say, now I will transform square wave voltammetry into a sort of square wave chronoamperometry. I take a constant potential, like in classical chronoamperometry, but now I impose pulses up and down. And then I measure the current at the end of these pulses and so on. And then square wave chronoamperometry, this is the theoretical response. And this is the response from the classical simple chronoamperometry, although already stable response, higher in the intensity, and so on. It can be modified even to more complicated way, like square wave chronoamperometry, but with different thickness of the pulses, which is also one powerful approach. Or I can really suggest a sort of hybrid techniques. For instance, I am going to merge square wave voltammetry with differential pulse voltammetry. And I will come to the potential modulation like this. And what is important for this technique is that out of the single experiment, measuring the current at different points, I can produce 7 voltammetric curves out of the single experiment, which already for people doing in chemometry, in deep machine learning, is already important. And now, in the last few minutes, I will lend myself and I come to the reality. I will say just a few words what I have done with the basic concept of electrolysis, Electrolysis of water. We know that electrolysis of water is generally important. We have seen data for production of hydrogen, then hydrogen in the fuel cells, and so on. But electrolysis of water is inspired some Russian scientists and then later Japanese people in the last 20 years, that simple electrolysis of water, pure water, in which drinkable water, without adding extra salt, electrolysis which is not easy, does not go fast, but still goes on. At the cathode, of course, traces of hydrogen are going to be produced, and the water at the cathode side is becoming alkaline due to simple reduction of water. Then we have a sort of alkaline water already enriched with the traces of hydrogen. Such alkaline water, people claim that even has a beneficial health benefit. It is healthy beneficial. And I have tested that water with respect to the antioxidant capacity. With the experiment, I will not go inside, And it's really like that. If I alkalized water to electrochemically by electrolysis to pH 9, for instance, the antioxidant capacity is obvious in comparison to the shorter electrolysis process coming to lower pH, or in comparison to the native water from which I have started the experiment. Electrolysis, of course, now is important that we produce silver nanoparticles. We know now silver nanoparticles are produced in tons, but that can be done now electrochemically, of course. Easily, in a pure water, simple anode, I can oxidize anode, producing so-called silver water, the most classical, the oldest antibiotics. But now, knowing a little bit nanochemistry, we can modify these particles, we can stabilize them, even we can enrich with a sort of antioxidant. For instance, here, glutathione, 3-peptide used as a stabilizing agent, but also as an antioxidant, which is interesting feature. And finally, electrolysis for some sort of metal deposition, which is rather unusual. I wanted to do the following. I wanted to deposit metals on the surface which is not conductive. That is already known. Non-conductive surface can be made conductive by carbon films, something like that. But I didn't want to do that, not carbon films, something else. Then I wanted to do metal deposition, electroplating, but without the concept of immersing material into the electrolytic bath, you know? Usually it is done, we have a solution, we immerse inside the material, and then we deposit. That is the classical approach. How to do that without any bath, without any deposition? I call that methodology electrochemical painting. And that is original photo from my laboratory, electrochemical painting. If I like to deposit copper at marble, for instance, originally it was like this, and now it's like this, metal on the marble. But of course, previously marble was made electrochemically conductive, without carbon, without conductive polymers. Simple electroless deposition practically of traces of silver deposition. And of course, that can be done with the wood. That is very exciting, you know, to make a wood metal composite, but real composite by electrochemical deposition. First, original wood, then covered with the traces of electroless silver deposition. The wood is becoming electrochemically conductive, electrically conductive. Then I deposit on that copper, and I deposit also, I can further deposit silver. It is sort of electrochemical painting, and I can explain to my colleagues, who are interested about that. So, dear colleagues, sorry, 2 minutes more. I hope that I have convinced in the power and beauty of electrochemistry, to which I dedicated an essay, not only real scientific article, but just essay on this subject. So thank you very much for your kind attention.
Yeah, the pulses method that you have developed. Have you tried it in a battery or supercapacitor? The one that you basically distinguish between the capacitive current and the other current.
No, not yet. We didn't work with the batteries, but that, of course, that I thought that this square wave chronoamperometric experiment would be used for the battery analysis.
We always try to do that by calculation, distinguish between capacitive current and other current. So if we can do that experimentally, that would be amazing.
Yeah, I think it is rather plausible. Yeah.
And this last slide. So how you deposit the sulfur basically to make these electrodes conductive in the first place?
Silver, not sulfur, silver. Yeah. Simple chemical redox reaction, silver nitrate and reducing agent. We just, we just like painting with different solutions, and then let dry, and then we have a really nanofilm of silver or network of silver nanoparticles. Then we have material. Then the copper, but without immersing in the solution. Again, with a sort of painting. We paint like a microelectrode, the material is a cathode. I have another electrode with a sponge, for instance, here, with a sponge. Another carbon electrode with the sponge. I take, for instance, copper sulfate solution, and when I touch now the material, now the circle is closed. And just on the place of touching, I deposit metal. I deposit copper. So that is why I can deposit without bathing inside.
Thank you, Professor, for this interesting talk. Just two questions. First, how to push young researchers to study electrochemistry nowadays? And the second one, how does this layer adheres to the surface? Does it stick really well to the surface, this methodology? Thank you.
Avni, thank you very much for this really in the focus questions. Of course, my story is very romantic about electrochemistry, you know. Electrochemistry is really simple and beautiful. But what's going on during electrochemical phenomena is difficult. It's really difficult, very complicated. And the art of teaching electrochemistry, I say like that, art of teaching electrochemistry will determine the future of electrochemistry. That is actually one sentence in this essay. The art of teaching electrochemistry. So it is up to us. It is our responsibility. Of course, critical question is how stable is this? This is difficult question, you know. This is proof of concept. We haven't done that in the direction to be really stable. How thick would be the film? Here you see silver is stable here. The wood became black somehow. It is stable. Not silver, but copper, we can scratch. Copper, we can scratch, of course.
Thank you. Thank you, Professor. Many thanks, Professor.
Okay. Thank you.